Good day everyone. So today we are going to discuss about the bucket sort algorithm. But before that, let me introduce my group. My name is Angel Lixinbi Mayor and I am Giselle Racho.
And I am Megan Clear. And I am Mariel Days Bantilio.
And now, let me show you our objectives. At the end of this video, you are able to know first, what is bucket sort algorithm? Second, how bucket sort algorithm works. Third, what is the time complexity of bucket sort algorithm? Fourth, how we apply sorting in real-life situations. And lastly, what are the scope and limitations of bucket sort algorithm? So now, let's proceed to our discussion. Bucket sort is a sorting algorithm that works by distributing elements into a number of buckets, sorting those buckets individually, and then combining them to get the final sorted array. Bucket sort is an efficient sorting algorithm, especially useful when the input is uniformly distributed over a range. There are 4 steps in bucket sort, and later on, we will show you an example of bucket sort. First is, we create a bucket. We must determine the number of buckets, and it is usually based on input size or range. And each bucket will hold elements within a specific range. Second is, let's distribute the elements. We iterate through the input array and assign each element to the appropriate bucket based on a calculated index. Third is, we sort individual buckets. Since buckets contain a small number of elements, insertion sort is typically used due to its efficiency with short list. Alternatively, any other efficient sorting method can be used. Fourth is, concatenate buckets. Let's gather all the sorted buckets in order to form the final sorted array.
Okay, so now I'm going to discuss the time complexity of bucket sort algorithm. So talking about time complexity, we usually have 3 cases to summarize time complexity. So first we have the best case. So the best case is big O of n plus k. Next we have the average case, that is big O of n into n. And finally, we have the worst case, that is big O of n. Here, n represents the total number of elements to be sorted and k is the number of packets. So let us understand all the 3 cases one by one. So first we have the best case. So the best case occurs when all the elements are uniformly distributed in the bucket with an equal number of elements in each bucket. If insertion sort is used to sort all the bucket sort algorithm, then the overall time complexity is big O of n plus k. O of n complexity is for making the buckets, and O of k complexity is for sorting all the elements after understanding the best case. Now we will see how the worst case occurs in the bucket sort algorithm. The worst case occurs when there are elements of close range in the array. They are likely to be placed in the same bucket. It makes the complexity depend on the sorting algorithm used to sort the elements of the bucket's complexity. Becomes worst when all the elements are in reverse order. And if insertion sort is used for sorting, the time complexity becomes O of n into n. And lastly, we will learn how the average case occurs in a bucket sort algorithm. The average case occurs when the elements are randomly distributed in the array. It occurs even when the elements are distributed in the uniform way. Bucket sort run at a linear time. The average case holds the true until the sum of bucket sort sizes is linear in the total number of elements. Next, we will see about the space complexity. So the space complexity of all the buckets of algorithms is big O of n plus k. Lastly, we have stability. So talking about stability, so yes, the bucket sort algorithm is stable after understanding the complexity of bucket sort algorithm.
Next is, we have the comparison with other sorting algorithm. First is, we will compare the counting sort algorithm. Bucket sort can be worked as a generalization of counting sort, and if each bucket has size 1, then bucket sort degenerates to counting sort. The variable size of a bucket sort allows it to use the big O of n memory instead of big O of m memory, where m is the distinct value that gives counting sort of big O of n plus m worst case behavior. Second is the quick sort. Bucket sort with 2 buckets is a practical version of the quick sort where the pivot value always selected the median value of the value range. Another means of the choosing the pivot in quicksort, such a randomly selected pivot, make it more resistant to clustering the input distribution. Third is the radix. Top-down radix sort can be a particular case of bucket sort where both range of values and the number of buckets has constrained the power of 2. This approach can accelerate the scatter phase since we only need to examine each element's prefix of bit representation to determine a bucket.
So now, we will show you the implementation of bucket sort in a computer program in Java. We have here an example which is a program report student grading system using bucket sort in Java. This Java program implements a grading system that accepts a number of student scores from the user, sorts this score using a bucket sort algorithm, and assigns and displays a corresponding letter grade for each score. And the grading scale used is if 90 to 100 grade is considered a grade A, then if 80 to 89 grade B, then if 70 to 79, which is grade C, 60 to 69, which is grade D, and if 60 below, it is considered a grade F. So now let's proceed in the code. Now in the first line, the package which organizes this class within a name package which helps manage related classes in larger projects, and then the imports which imports all the classes from the Java utilities package, including like the scanner for reading the input, the list and array list for the bucket storage, and then the public class bucket sort which defines the main class, which is the bucket sort algo. All methods and logic of the program are encapsulated within this class. Next is the public static void. To sort an array of integers like the student scores using the bucket sort algorithm. In this conditional statement, it checks if the array is empty. If true, it exits the method to avoid unnecessary processing. And in these next lines, it iterates through the array to determine the highest score. This helps in bucket distribution. In the next lines, it calculates the number of buckets using the square root of the array length, and it declares an array of lists to store the scores. And then the next is, it initializes each bucket as a new array list. And in this loop, it maps each score into a specific bucket based on its relative value using a proportional index formula. And for the next lines, it sorts each bucket using a Java's built-in collection .sort method. And for the next lines is, it concatenates all sorted buckets back into the original array. So in grade calculation method, the public static string which converts a numerical score into a letter grade, which I explained earlier the conversion. It applies conditional checks to return the correct grade string based on the scores. So next is the main method, which serves as a program's entry point. It handles user input, sorting, and displays the result. Next is the scanner. It creates a scanner object to create a user input from the console. And then next is we have to print out, which informs the user of the grading system before collecting the scores. So we have an overview. And then next is we also need to print out prompts. It prompts the user to input the number of students, like scores in a variable n. And then in these lines, it initializes an array scores to store each student's score. It uses a loop to prompt for and collect individual scores. Now in this line, the bucket sort calls the bucket sort method to sort the scores in ascending order. Now for these lines, display sorted scores and grades, It displays the sorted grades and their corresponding grades using a loop and the getGrade method. And lastly is scanner.close. It closes the scanner object to free up system resources. So that's it for the codes. Now we will show you how to run the program. You will see first the grading system, and then it asks the number of students you are gonna sort. For example, 5 students. Then you're gonna enter each of those scores for those students. For student 1 is 67, the next student is 54, next is 78, next is 97, and lastly for the last student is 80. So, after you input the scores, it shows the sorted score and the letter grades. So in this Java program, it demonstrates the use of bucket sort algorithm for sorting student scores efficiently. It also introduces a simple grading system that assigns letter grades based on numeric ranges. The combination of sorting and grading allows for easy analysis of student performance. So that's it for the simulation of bucket sort algorithm.
So now let's proceed to its bucket sort algorithm strength. Evaluating bucket sort through runtime measurement and input size scaling gives a clear picture of its speed and how well it scales with larger GPA datasets. Distribution sensitivity tests reveal the algorithm's ability to handle various data patterns, which is important since GPAs may not always be uniformly distributed. Memory usage evaluation ensures that the algorithm uses resources efficiently, avoiding excessive space consumption. Correctness validation confirms that the sorting results are accurate by comparing them to trusted methods, while stability checks guarantee that equal GPA maintain their original order, preserving fairness. Together, these evaluation methods provide a comprehensive assessment, making bucket sort both efficient and reliable for practical GPA sorting applications. Despite its efficiency, bucket sort has several limitations. First is distribution sensitivity. It performs best with uniformly distributed data. Skewed data can cause some buckets to become overloaded, reducing performance. Second is bucket count selection. Choosing too few or too many buckets affects both speed and memory usage. There's no fixed rule for the ideal number. Third is requires no range. The algorithm needs prior knowledge of the data range, which limits flexibility for unknown or dynamic datasets. Fourth is extra memory usage. Buckets requires additional memory, making it less suitable for large datasets or memory-limited systems. And lastly, the complex stability handling. To ensure stability, a stable sort must be used within each bucket, adding complexity. So these factors must be considered when applying bucket sort, especially for real-world datasets like GPA scores. Lastly, let's talk about its limitation and challenges. Despite its efficiency, bucket sort has limitation, especially when the input data is not uniformly distributed, which can cause some buckets to become overloaded and degrade performance to quadratic time. Choosing the right number of buckets is challenging and can significantly affect both speed and memory usage. Too few buckets lead to inefficient sorting within buckets, while too many increase overhead. The algorithm requires prior knowledge of the input range, making it less flexible for data without clear boundaries. Additionally, bucket sort uses extra memory to hold bucket, which can be costly for very large datasets or memory-constrained system. Finally, implementing a stable and efficient sorting method within each bucket is crucial, but can add complexity to the overall algorithm.
Thank you for listening. Bye!